that we have to talk about is the IAR filter design and the structure as well. Okay, so like we wrote for the FIR filter, we designed the FIR filter coefficients and also learned how to draw a few structures in the FIR filters. The same way, we are going to learn methods to design the IAR filter and also draw its structures. Okay. So the IAR filter is a recursive filter. We have talked about this before. So what is a recursive filter? A recursive filter is one whose output will be a function of input, past inputs, okay, and past outputs. So these past outputs are not present in an FIR filter, isn't it? FIR filter is therefore a non-recursive filter which depends only on the input and the past values of the input. Whereas IAR filter is a recursive filter. It depends on the past output values as well. Okay, so the difference equation for an IAR filter can be written in general as summation ak y of n minus k from 1 to n plus summation k0 to m bk x of n minus k. So you can see that we have past outputs here, also the past and the present inputs in the difference equation for an IAR filter. Therefore, for such a filter, when you take the Z transform and write the transfer function of the filter, okay, which can be straight away done, right? You should be much familiar with that now. It will be of this form, Z minus K divided by 1 minus summation ak z bar minus k from 1 to n. So you can see that the transfer function of an IAR filter has a numerator polynomial as well as a denominator polynomial in Z. So this means to say, you know that the numerator polynomial corresponds to the zeros of the transfer function and the denominator polynomial corresponds to the poles of the transfer function, isn't it? Therefore, in an IAR filter, both zeros and poles would be existing, right? In such cases, the stability of the filter becomes a problem. Okay, so in that case, we'll have to look at the location of the poles in the transfer function. If all the poles lie within the unit circle in the Z plane, only then the system is going to be stable. Okay, so this condition we have learned before in signals. Therefore, depending on the location of the poles, the system could be stable or it could be unstable also. Whereas in FIR, that was not the case. The system was always stable because there was no poles at all. The stability does not depend on the location of the zeros. It depends only on the location of the poles. And since there are no poles in the transfer function of the FIR, it's always stable. Whereas in IAR, it doesn't happen that way. So these are the two major differences between IAR and FIR. But still, there are more. So as we are designing, you can see the methodology of designing the filters is different. The orders that you obtain, the order of the filter that you obtain, two cases are different. Okay. Usually IAR filters have a lesser order when compared to an FIR filter. Practically, when you design the filters, which you'll also be doing it in your lab programs, you can observe there that the IAR filter has a lower order generally. Whereas an FIR filter, the order will be very high. Okay, the order of the filter will be very high. In an IAR filter, there are two kinds actually. Two kinds of IAR filters. Butterworth filter is one category and Chebyshev filter is the other type of IAR filter. Okay, so Chebyshev, again we have two kinds of Chebyshev filters. One is called as type 1 filter and the other is type 2 filter. Okay, type 1 and type 2 filters. So what is the difference between these filters is the way in which the frequency response of the filter is defined. Okay, a Butterworth filter, when we design a Butterworth filter, right, it has a monotonic passband. What do I mean by saying monotonic passband? Is it has a flat passband. Otherwise, there could be ripples in the passband and the stopband. So two kinds of responses, monotonic response and it could have ripples in the passband and the stopband. So Butterworth has a monotonic response, right? And generally the transition band of a Butterworth filter will be little large. Okay, it will be a gradual transition and then it comes down to zero. So almost flat in the passband. Okay, so it has a monotonic passband and stopband and a wide transition band, a Butterworth filter. Chebyshev filter, on the other hand, will have ripples in the passband or in the stopband. Type 1 filter has ripples in the passband and a monotonic stopband. Okay, whereas type 2 filter has a monotonic passband and ripples in the stopband. Okay, so that is the difference between Butterworth and Chebyshev filters. So these are the most popular kind of IAR filters that are available. So first what we'll do is we look at the kind of filter specifications that will be given to you in the IAR filter design problem. It is slightly different than what we wrote for the FIR filter. Okay, so the filter specifications that will be given to you in the problem, we should be clear with that. What is that? And then we will then take a particular case, that is the Butterworth filter we are going to take first, and then see how to design the Butterworth filter. Okay, then one more thing. Whether we talk about a Butterworth filter or a Chebyshev filter, you can design a low pass in this, high pass, band pass, and band stop. Okay, all the four kinds of filters can be designed. But one thing with the IAR filter, how we design an IAR filter is we first design a prototype. Okay, so we first concentrate on designing a prototype. So what is this prototype? This prototype is an analog low pass filter. Okay, whether Butterworth or Chebyshev. I'm talking about IAR filters in general. So the design procedure for an IAR filter is we first design the prototype. What is the prototype in this is an analog low pass filter is considered as a prototype in the IAR filter design. So be very cautious of this word. We are designing an analog filter first. But what is it that is desired for us? We want to design a digital filter finally. Okay, but we only concentrate on designing an analog low pass filter first. Okay, and then we are going to convert this analog filter into the corresponding digital filter. By applying transformations. Okay, by applying various transformations. So these are called as analog to digital transformations. Okay, analog to digital transformations. So basically there are four kinds of such transformations. We have something called as the backward difference method, then matched Z transformation, okay, matched Z transformation, then bilinear transformation, and impulse invariant transformation. Shall I expand this BLT? Okay, this is called as bilinear transformation. Okay, so in an IAR filter design, we always design an analog low pass filter first. Whatever the filter is given to you, whether they give you a high pass, they give you whatever filter specifications, first the analog low pass filter is designed. So this acts like a prototype. And if you have to design the corresponding digital filter, you will have to apply some kind of analog to digital transformation. We have 4 kinds in this transformation: backward difference, match Z transform, bilinear transformation, and impulse invariance transformation. Okay, so these are the 4 kinds of transformations which we can apply to convert an analog filter into the corresponding digital filter. Among this, bilinear transformation is very popular. Okay, because it has its own advantages. We'll see what it is. So bilinear transformation is very popular, and then is the impulse invariance transformation. Okay. So BLT is usually the most popular technique of converting an analog filter to a digital filter. Then, how to design a high pass, band pass, and a band stop filter. Okay, again, the analog low pass filter forms the prototype for us. Okay, the analog low pass filter is the prototype. So this filter, we can apply again something called as analog to analog transformations. Okay, we have something called as analog to analog transformations to convert this low pass to high pass or band pass or band stop. Okay, so what is this transformations? Is nothing but you just see ways and means of substituting for the angular frequency omega so that you convert it to the corresponding other filters. That's all. Okay, so they have derived these transformations before itself. They have derived these transformations which will help us convert one filter to the other. That's the only thing. Okay, so once you have applied the analog to analog transformations to convert into these filters, these are still analog in nature, right? These are still analog in nature. After this, you apply the A to D transformations, that is this analog to digital transformation to convert it into a digital filter. Okay, is that clear? So whatever the kind of filter that we want to design, digital low pass or digital high pass or digital band pass, whatever, we have to first start with the analog low pass filter. We first design the analog low pass filter and then apply suitable transformations to convert it to the other types. This is the procedure we follow for an IAR filter. Okay, so what is it that we have to concentrate now is how do you design this analog prototype, analog low pass filter prototype. That is what we have to concentrate now, whether it is Butterworth or it is Chebyshev. So when I say to design the analog low pass filter, yes, we can either derive the transfer function, you know that now. For a filter design, you can either derive the transfer function or the filter coefficients h of n, right, or the frequency response, isn't it? So that's what we are going to do here. We are going to be designing the frequency response of the analog low pass filter. Okay, we'll derive the frequency response because these transformations are based on substitutions for this omega, right? So therefore, we are interested in designing the frequency response for the analog low pass filter prototype. Initially, it might look like this design is little complex, the IAR design, but it is actually not. Initially, when you start deriving things, it looks like you have too much of derivations and too much to remember, but then there is not much actually. Again, when I say it's a very mechanical way of, the filter design procedures are very mechanical. Once you have the procedure on hand with you, then it's like, there's nothing that is going to be different. It becomes very mechanical. But the thing is, a lot of computations will be there. Okay, the computations are quite huge in case of the IAR filters or FIR filters also for that matter. Okay, so first, before we start off with the design, first let's write down what the specifications are for an IAR filter. How is it that they're going to give you the specifications? Because these notations are important for us whenever we are discussing. Okay, the notations are very important. So let's concentrate on that first, and then we'll see how to design the other things. Okay, so the analog filter specifications, and if the digital filter specifications are given to you, we'll also see how you have to convert them to analog for the purpose of the design. That we will do when we come to the problems. Okay, so now the first thing is how the analog filter specifications will look like. What is specifications? Passband edge frequency, stop band edge frequency, passband ripple, and stop band ripple. Those are the specifications. Okay, we have written this for FIR filter also. Yeah. So now for an IAR filter. So let's assume that, so we am writing the magnitude response of an IAR filter. So we assume that there are ripples in the pass band and also ripples in the stop band. Okay, because for Butterworth it is different, Chebyshev it is different. So now we are writing in general. We are writing the specifications in general. Accordingly, for Butterworth and Chebyshev, we take whatever is the required specifications. Okay, so since I am writing the magnitude here, the magnitude varies, the ripples in the pass band varies between then the ripple in the stop band, that is denoted as delta S. So delta S is the stop band ripple. Delta S is the stop band ripple. Okay, so this is 0. The pass band edge is denoted as omega p. See, all these notations are for the analog filter. Okay, that's why we are writing this omega. So omega p is the pass band edge frequency, omega p, and this one, edge of the stop band, is omega s. Omega s is the stop band edge frequency. So this is the pass band, this is stop band, and this is transition band. Transition band. Okay, so those are the analog filter specifications, the 4 parameters that will be given to you. Delta P, delta S, omega P, and omega S. So mathematically, how do we write the frequency response? The magnitude frequency response, how do we write it mathematically? Because sometimes they also give you the mathematical representation. From that you may have to pick out the 4 parameters. Okay, so you should know the mathematical representation as well. So how we write the mathematical representation is, just move it here, write it here itself. So the mathematical representation is written as, now see, the magnitude of h of j omega, right, is varying between, in the pass band, that is in the frequency 0 to omega p, it varies between 1 and 1 minus delta p, right? The magnitude varies between 1 and 1 minus delta p. So it's greater than 1 minus delta p, but less than 1. The magnitude is less than 1 and greater than 1 minus delta p. In what range? for omega between the interval 0 to omega p. That is in the passband. That is in the passband. Okay, I will also put a magnitude here because you know the magnitude response is always symmetric, right? The response will be like this for a low pass filter. That's how we draw. It is symmetric about the origin. So we just write that as magnitude. We don't worry plotting the left hand side because it's not required for us. This is the definition of low pass frequency response is sufficient if you plot it this way. Then in the stop band, the magnitude is less than delta S, right? The magnitude is less than delta S. So magnitude of j omega is less than or equal to delta S, less than or equal to delta S. So this is where for magnitude of omega greater than and equal to omega S, greater than or equal to omega S. So in the stop band for omega above omega S, greater than omega S, the magnitude will be less than delta S. Magnitude will be less than delta S. That is the, so this is how mathematically we write the frequency response of an analog low pass filter. So sometimes what they do is they give you this, okay? Instead of giving the parameters straight away, they could give you this. So from this representation, you should be able to pick up the 4 parameters. That's the point. Then we also define the gain here in decibels. Okay, so sometimes the value is given in dB. The gain of the passband and the stop band will be given in decibels. So how do you convert that to decibels? Okay, how we convert this to decibels is we denote the passband gain by Kp, and that is given as 20 log of 1 minus delta p. 20 log of 1 minus delta p. So this will be in decibels. Okay. And since 1 minus delta p is a quantity less than 1, you will expect Kp to be negative. Kp will be negative. Okay. Then stop band gain. Stop band gain is denoted as Ks, and that is given as 20 log of delta S. 20 log of delta S. That is the stop band gain. Stop band gain. And in the AR design, we use all these parameters, Kp, Ks, that is the decibel values we use. So the conversion of the decibels is required for us here. So Kp is 20 log 1 minus delta P and Ks is 20 log delta S. Okay, so those are the general filter specifications that will be given to us. Now we'll take the Butterworth filter, the first filter, and write down the frequency response of the Butterworth filter. So we are going to look into all the characteristics of the Butterworth filter, how exactly it is, how many poles are located or obtained in the Butterworth filter design. How do you determine the poles? Okay, you have to only find out the poles. So once you write the poles, how do you write the transfer function? Okay, all this constitutes the design of the Butterworth. So everything from scratch needs to be done. So first let's understand the characteristics of the analog Butterworth filter, and then we'll write down the design procedure. So characteristics of a Butterworth filter. Analog, of course. Characteristics of a analog Butterworth filter. So the Butterworth filter, like I told you, has a monotonic pass band and stop band. and a wide transition band and a wide transition band. So magnitude of h of j omega will be something like this. Okay, this is for an order 1, let us say, a first order filter. It starts with 1 here. Okay, as the order of the filter increases, the transition band becomes more steeper. Okay, the transition band becomes more steep. So if for n equals 10, if I draw a Butterworth filter, it would be something like this. Okay, this is for an order 10 filter. An order 10 filter. So as the order of the filter increases, the transition band becomes more narrower. Okay, it becomes a steep transition from the pass band to the stop band. So there are no ripples in a Butterworth filter in the pass band and the stop band. And a Butterworth filter is an all-pole filter. So when I say all-pole filter, that means there are no zeros in the transfer function, only poles are located. It's an all-pole filter, so only the poles are located in case of a Butterworth filter. Okay, then the cutoff frequency. Cutoff frequency is where the magnitude is 1 by 2, 3 dB cutoff, right? That's how we take minus 3 dB cutoff. That is the cutoff frequency for a Butterworth filter. Now see, when the specifications for the Butterworth filter is given is with respect to omega c. So if omega c is given to you, we also have means to convert it to omega p and omega s. Okay, but the cutoff frequency will be defined. That is, the frequency response of a Butterworth filter has the parameter omega c in it. So now let's write down the expression for the magnitude frequency response for a Butterworth filter. That is given as magnitude of h of j omega is given as 1 by 1 plus omega by omega c to the power 2n whole raised to the power 1 by 2 under the root. So omega c is the cutoff frequency or minus 3 dB frequency, and n is the order of the filter. N is the order of the filter and omega c is the cutoff frequency. So that is the magnitude frequency response for a Butterworth filter. Now what we'll do is we'll write down the transfer function of this filter. Okay, so transfer function for a digital filter, when you write it, is h of z, isn't it? Z transform we have to take. But in case of analog filter, the transfer function is h of s. H of s. So we'll write down h of s and we try to design a stable IAR filter. So how we have to do that is what we have to see here. So next what we will do is we are going to normalize the filter. Okay, we are going to normalize the filter. What do I mean by saying normalize the filter is we will make the cutoff frequency omega c to be equal to 1 radian per second. 1 radian per second. See, first of all, we are designing an analog filter prototype. In that, we are going to start with a normalized filter. Okay, normalized filter wherein we make omega c, okay, normalized filter wherein we make omega c equal to 1 radian per second. So why we do this is because the design becomes simple for us. Now if you look at the expression of h of j omega, it's very difficult for us to analyze where the poles are. First of all, that is important. Okay, that's the first step. We have to decide or we have to find out where the poles are located and then select the poles which will give us stability. Okay, and then design the transfer function of the filter. Okay, so with this above expression that you have, this expression, it is quite complex to design the filter. That is why we normalize the filter, make omega c equal to 1, design the filter, and then again convert it back to the filter with a cutoff frequency of omega c. So omega c equals 1, we are going to substitute in the above expression. So let us call the transfer function of an normalized filter with this notation Hn. So n indicates the normalized filter. Hn of j omega, so magnitude, is equal to 1 by 1 plus omega to the power 2n under the root. So omega c equals 1 is what we have done. So normalized filter we will consider. Now, Hn of j omega is a complex quantity, isn't it? Hn of j omega is a complex quantity. So magnitude of a complex value, you know, can be written as magnitude of a plus jb can be written as a plus jb into a minus jb. That is the complex value multiplied by its conjugate, isn't it? That will give you a square plus b square, which is nothing but, okay, the magnitude square. The magnitude squared can be written as the complex quantity into its conjugate. So that's what we will do here now. We have a square root here. So let's square both the terms, both sides. So this is what we are going to obtain. Magnitude square equals 1 by 1 plus omega to the power 2n. Then magnitude square, I will write it as Hn of j omega into Hn of minus j omega using this relationship. So that is equal to, right hand side remains the same, omega to the power 2n. Okay. Now to convert the frequency response into the transfer function, of analog, we will substitute S is equal to j omega. We will substitute S equals j omega. So what is omega then? S by j. Omega is S by j. So let us substitute that here. Hn of S into Hn of minus S equals 1 by 1 plus S by j to the power 2n. S by j to the power 2n. So that is the transfer function. But still we have not written just one transfer function. On the left hand side you have Hn of S into Hn of minus S. So it's like a product of two transfer functions. Okay. So this transfer function which we have written, if you have to find the poles of this transfer function, we have to equate the denominator polynomial to 0, isn't it? That's how we find the poles of a transfer function. So let us equate the denominator polynomial 1 plus S by j to the power 2n to 0. Then how do you find the poles? You have to find out what is S. Correct? The location of S gives the location of the poles. So equate the denominator polynomial to 0 and find what is the value of S. Okay, so let's do that. So S by j whole power 2n, and put minus 1 onto the other side, right? Then we'll put j also onto the other side. So S to the power 2n equals minus 1 into j to the power 2n. J to the power 2n. Correct? So how many poles do you expect here? 2n poles are there in this transfer function, isn't it? S power 2n. That means there are 2n poles in the transfer function. So 2n also, that power 2n also we are going to remove. So we'll take the 1 by 2nth power. So minus 1 to the power 1 by 2n into j. Because j power 2n you have, if you take 1 by 2nth power, that will get cancelled and you will be remaining with j. So we have a total of 2n poles in this transfer function. Now we'll have to find what is the value of this S. Okay, what is this S? For that, what we'll do is, we will write minus 1. We will write minus 1 as e to the power j pi, e to the power j pi into an odd number, 2k plus 1. Why am I writing it like this? Now let's say you put k equals 0. Okay, what do you get? E to the power j pi. What is e to the power j pi? Cos pi plus j sin pi, that is minus 1. Correct? You put k is equal to 1. So 2 plus 1, 3 pi. E to the power j 3 pi. Again cos 3 pi is minus 1, sin 3 pi is 0. Again you get a minus 1. Similarly, k equals 2. Right? So an odd power, e to the power j pi, an odd value will always be equal to minus 1. So I want to use this for substitution here for minus 1. Okay. So to be very specific, k I'll put from 0, 1, 2, 3, etc. up to 2n minus 1. Up to 2n minus 1. Because we have a total of 2n poles. Okay. That's what we are going to substitute for minus 1. For j, what will we substitute for j? Can I write this as e to the power j pi by 2? So why we are writing it as an exponential? Because we want the poles to appear in the polar form. That's all. So that we can locate them, right? It should be a complex value, a plus jb, either in the rectangular form or in the polar form. Anything will help us locate the poles in the complex plane. And if you look at these terms, straight away it's not possible, right? Locate all these poles on the S-plane. We need a proper equation to find the poles. So that is why we are trying to representing it in the polar form. So that's why we are writing it as an exponential. So minus 1 is written as e power j pi into 2k plus 1 to the power 1 by 2n, and j is written as e to the power j pi by 2. E to the power j pi by 2. So now we can combine the exponentials, both the exponentials. So if you combine that, e to the power j, okay, j pi into 2k plus 1 divided by 2n plus pi by 2, plus pi by 2, the whole thing. Okay, further we can simplify this and write it as e to the power j into 2k pi by 2n, that is pi k by n plus pi by 2n plus pi by 2 plus pi by 2. So now we have got the location for the poles S. For the poles S, where your k varies as 0 to 2n minus 1, because you have 2n poles. So let's denote this poles as Sk. It becomes easier for us to locate the poles. Sk. So how do you think the poles are located now? If you look at this expression, 1 e to the power j theta form. Isn't it like that? R e to the power j theta form. R is 1. That means the poles are located on an unit circle. The poles are located on an unit circle. Okay, in the S-plane. In the S-plane. At what angles? At an angle of this. At an angle of this. So if you put k equals 0, you get the first pole. You put k equals 1, you get the second pole. K equals 2, you'll get the third pole, and so on up to 2n poles you can calculate. Isn't it? You can calculate 2n poles like this using this expression. And we can locate all the poles here, right, on the unit circle. You can locate the poles on the unit circle like this. Okay. Now, if the value of n is 2, let us say, you're going to of the S-plane and 2 will be on the right half of the S-plane. That's how they will be located. They will be symmetric. Okay. If your value of n is 3, you have 3 poles on the left and 3 poles on the right. If your value of n is 4, you have 4 poles on the left, 4 poles on the right, like that. Because you have double the number of poles, 2n poles you have. So if your order is 2, if it's a second order filter, 2 poles on left and 2 poles on the right. That's how it will be located. So what is this now we have obtained is the location of the poles for this transfer function. Isn't it? We have obtained where the poles are located for this transfer function. So using the expression of S, it's easier for us to locate the poles, and this is how the transfer function is. Now what we'll do is we have two transfer functions here, Hn of S and Hn of minus S. Isn't it? You have Hn of S and Hn of minus S, product of two transfer functions you have here. So I don't need these two transfer functions. I'll just pick out one transfer function from this, and since I am interested in designing a stable filter, okay, I am interested in designing a stable filter, we will pick out those poles which give us stability. Now, in an analog filter or in an S-plane, what is the condition for stability? The condition for stability is the poles should lie on the left half of the S-plane. Analog filter, left half of S-plane. So now here you have two sets of poles, isn't it? We have poles which are lying on the left half and poles which are lying on the right half. And since we are interested in designing a stable filter, let us take all the left half poles, and assign it to Hn of S. And you can take the right half poles and assign it to Hn of minus S. Anyway, we will not use this transfer function. Is that clear? On the left hand side, you have a product of two transfer functions, Hn of S and Hn of minus S. I will just pick out Hn of S from this transfer function and assign all the left half poles to this transfer function. So n poles you're going to assign to this transfer function. Why we are picking only the left half poles? Because that gives me stability. Is it right? So Hn of S is my desired transfer function of the Butterworth normalized filter, to which I will assign all the left half poles. What is this notation? Product. Like we write this for summation, this is for the product of the terms. So product of all the poles, S minus Sk. That is how you denote the poles, right? 1 over S minus S naught into S minus S1, right? Into S minus S2 and so on. Product of the poles. So all we are going to assign it to Hn of S, and that will be my desired Butterworth filter transfer function. Butterworth filter transfer function. So this polynomial that you obtain in the denominator is denoted as Bn of S. It is denoted as Bn of S, and it is called as the Butterworth polynomial. It is called as the Butterworth polynomial of order n. The denominator polynomial that you obtain by multiplying all the left half poles is called as the Butterworth polynomial of order n. So actually, this Butterworth polynomial is calculated for all the orders starting from n equals 2, 3, 4 like that, and an annexure will be created actually. So initially they were allowing these tables to be used in the exam because the computations are too large, but then they stopped. So in your filter design, you will have to find out this Butterworth polynomial. You will have to find out the Butterworth polynomial. Okay. So how do we find out this Butterworth polynomial for different orders? You learn for one or two, it will be the same for the others. And for lower orders, you can also remember these polynomials actually, because they are quite simple. So this will be part of the design. Okay, it will be part of the design of the Butterworth filter. So for n equals 2, I will show you how to find the Butterworth polynomial. We'll find all the poles, locate the poles first, and then write down the Butterworth polynomial. Okay, so here in this expression, what is important for me is this expression of the location of poles. You have to remember this, Sk. We can also write this as Sk equals e to the power j theta k, where theta k is this expression. So now for second order, for n equals 2, let us derive the poles where they are located and also write down the Butterworth polynomial which is required for the design. Okay. So for n equals 2, Sk equals e to the power j theta k. So your k will be 0, 1, 2, 3, 2n minus 1. Second order, 4 poles will be there. So let us find theta k now. Theta k, pi by 2 plus pi k by 2 plus, I'm sorry, let me write the expression first. So that is pi by 2 plus pi k by n plus pi by 2n. Let's substitute the value of n. So pi by 2 plus pi k by 2 pi by 4. Pi by 4. So pi by 2 plus pi by 4 will be 3 pi by 4. So that is 3 pi by 4 plus pi k by 2. Okay. Now let's put k equals 0. So you'll find theta 0, the first pole, the angle of the first pole. So k equals 0, that means this is 3 pi by 4. 3 pi by 4. How do you find the location of the pole? S naught is e to the power j theta naught, which is nothing but cos theta naught plus j sine theta naught. Again, since you have pi here, you keep the calculators in the radian mode. Then you can substitute pi as pi. If your calculators are in degree mode, then pi should be replaced with 180. 3 pi by 4. 3 pi by 4. So cos 3 pi by 4 plus j sine 3 pi by 4. You can find those values. Minus 0.707 plus j 0.707. That is where the first pole is located. Similarly, k equals 1. If you put k equals 1, you will get theta 1, that is 3 pi by 4 plus pi by 2. 3 pi by 4 plus pi by 2. So that will be 5 pi by 4. 5 pi by 4. So S1, the location of the second pole. Cos 5 pi by 4 minus 0.707, sin 5 pi by 4 minus j 0.707. Okay. So similarly, for k equals 2 and k equals 3, we can go on finding the values. But let's locate the poles first on the S plane. So you can see that you just have to find the first n poles, that's all, for your transfer function. You don't need the remaining. So I don't have to calculate for k equals 2 and 3 here. Okay. So we locate this poles now. We locate the poles here. So the poles will lie on the unit circle, isn't it? So where is your first pole? S0 at an angle of 3 pi by 4, or that is minus 0.707 plus 0.707. So that's located here, isn't it? This is S0. So this is sigma j omega S plane. Then k equals 1 minus 0.707 minus j 0.707. Where is that located? It will be here. This is your S1. So 2 poles we found out, right? Similarly, if you had found out k equals 2 and k equals 3, you will find that the pole is located here, S2 and S3. S2 and S3. Okay, but why I didn't find S2 and S3 is I am only interested in the poles which are lying on the left half of the S plane. The poles which are lying on the left half of the S plane. I am not concerned about the poles which are on the right half of the S plane, because for me I'll take only the left half poles so that it gives me stability, the filter that I'm designing, and assign it to Hn of S. Okay, so I am interested only in the first and second pole. So if it's a second order filter, you have to find the first 2 poles. That's all. You don't even have to go to these calculations. You don't even do it in the design procedure also. So now to find the Butterworth polynomial, so what is your Butterworth polynomial here? B2 of S will be S minus S0 into S minus S1. S minus S0 into S minus S1. Yes, you can write down the values of S0 and S1 and multiply. Write down the values of S0 and S1 and you can multiply the 2 polynomials. You see that you'll obtain it as S square plus 1.414S plus 1. That is what you get when you multiply the 2 polynomials. So like this for n equals 3. Okay, again you'll have to write down your theta k value, substitute k equals 0, 1, 2, right? And then write down all the pole locations, take the first 3 poles and multiply like this to get your third order polynomial. For n equals 4, fourth order polynomial, and so on. So I'll give you the polynomials for third order and fourth order, but I'll leave it as an exercise for you people to find the location of the poles and find this polynomial. You can do it and see. Okay. So B3 of S, the third order polynomial, you're going to obtain as S plus 1 into S square plus S plus 1. Someone is unmuted. Mute ಮಾಡ್ಕೊಳ್ಳಿ. S plus 1 into S square plus S plus 1. Okay, and whenever you're multiplying the 2 poles, you get complex conjugate poles always. Now in this case also, you can observe that S0 and S1 are complex conjugate. So if you multiply two complex conjugate poles, you will get a real polynomial like this. So we don't have to multiply the entire polynomial and keep it in terms of s cube like that. You can keep it like this also. Usually in the appendix, when you see the Butterworth polynomial, this is the form that you're going to get. Similarly, B4 of S, you will obtain that as S square plus 0.766S plus 1. So when you multiply two complex conjugate poles, you're going to get values like this, poles like this. That will be the fourth order Butterworth polynomial. Generally, you cannot expect a problem beyond the fourth order. They have not asked so far. Usually it's a second order or a third order problem. Okay, mostly because it takes time to solve this. So like I told you, you can remember these polynomials and write it in the exam. But I also suggest that you write the expression for the poles. Okay, that is which one? Coming back to this, you write down this expression for the poles. Okay, this one which you have written. Write this expression, and write the values of k that you're going to substitute. Okay, and just show some calculations here because they should know that you have done some calculations there to find out the polynomial. Okay, so put the values like this and just show a few calculations, but then you can write down the polynomial once for all. Right, I am very sure that it's easy to remember these polynomials, isn't it? It's very easy to remember the polynomials. At least the second order and third order can be easily remembered. You can just write them. It doesn't matter because a lot of calculations are there to find the order and cutoff frequency also. We are still not done with the filter design. If you observe this frequency response, we are still with the pole locations. If you observe the frequency response of the filter, okay, the very first expression that we wrote, okay, this one, you can see that we have to find out the order and cutoff frequency also. We need to find expressions for n and omega c. What should you substitute? How should you find out the order of the filter? What is the cutoff frequency? That we need to find out. Just the location of the poles we have found out now. That's all. Okay, so that n and omega c also needs to be found out. We have to derive expressions for that. So is that clear? To write down the Butterworth polynomial, like I told you, write all the expressions, write all the equations correctly, show a few calculations, and then write the polynomial straight away. It doesn't matter. Now, let's derive the expression for order and the cutoff frequency of a filter, of the Butterworth filter. Okay, so now let's consider a low pass Butterworth filter, which is the prototype that we always talk about. And let me write the decibel scale here. So 20 log magnitude of h of j omega. So we are writing the decibel scale, and since it's a Butterworth filter, it has no ripples in the pass band or in the stop band and has a very smooth transition band. Okay, so since you're starting, you're writing the decibel scale, this value will be 0. The pass band gain will be Kp and the corresponding frequency is omega p. The stop band gain is Ks and the cutoff frequency is omega s. Okay, so this is the specifications of an analog low pass Butterworth filter. So how do we write the frequency response mathematically? So 20 log magnitude of h of j omega. So why I'm writing 20 log? Because this is the decibel scale. So even the magnitude also can be given to you. Any one can be given. But now for the derivation of the order and the cutoff frequency, the decibel scale is quite convenient. That is the reason why we also can write mathematically the expression of the decibel scale. So previously when I had shown you the specifications, here in place of this 20 log, we had just magnitude of h of j omega, isn't it? Now I am writing 20 log because this is a decibel scale. So 20 log magnitude of h of j omega lies between 0 and kp, isn't it? The pass band is between, the magnitudes are between 0 and kp. And where is this? For magnitude of omega less than or equal to omega p. Less than or equal to omega p. So that is in the pass band. In the pass band. For omega less than omega p in the pass band, this is how the value of the magnitude is going to be. And 20 log magnitude of h of j omega is less than or equal to Ks, that is the stop band attenuation, Ks. Where is this? In the stop band, that is omega greater than omega s in the stop band. So these are the specifications that we start off with. Now what is our aim is we need to design the filter. In turn, we need to find the transfer function of the filter. Okay. So if you need to find the transfer function of this Butterworth filter, so what was the frequency response that we first wrote? Magnitude of h of j omega, we had written this as 1 over 1 plus omega by omega c to the power 2n raised to the power 1 by 2. This is the expression we started off with, right? So what we have discussed so far is once you know the order of the filter, that is you know what is n, then you can go on to find the poles of the filter, you know the expression for that, and just consider only the left half poles and then write down the transfer function, isn't it? And that too, this we know for a normalized filter. Normalized low pass filter. What is a normalized filter? Wherein you have made omega c equals 1 radian per second. But here we have to actually design a filter with this magnitude response. So what are the two unknowns that we have here? It is the order of the filter and the cutoff frequency, because you cannot write this transfer function for the given specification, isn't it? That is a normalized prototype that we have written, normalized filter, and that is a prototype for us in case of the IAR design. We need to design a filter with this cutoff frequency omega c. That is the desired one, which we have to write. Okay. So once you obtain Hn of s, then we can apply the suitable transformation to get the filter with a cutoff frequency of omega c. But before that, you need to know what is capital N, isn't it? Until you know what is the order of the filter, you cannot find the poles. It's not possible for you to find the poles. So the very first design step will be to find the order of the filter. So what is that expression for the order of the filter that we have to use here for the Butterworth filter is what we have to derive now. Okay. So this expression that I have written here for the frequency, that is the magnitude response, let us take 20 log 10 on both sides. Let's take 20 log 10 on both the sides. So that will be, so if I take 20 log to base 10 on both sides, it will be equal to 20 log of, so if I write this in the numerator, the term which we have here in the denominator, 1 plus omega by omega c to the power 2n, it will be minus 1 by 2, isn't it? Minus 1 by 2. Then this minus 1 by 2 can be brought down along with this term 20, isn't it? 20 log a to the power n, that n can be brought down. So that will become minus 10 log of 1 plus omega by omega c to the power 2n to the power 2n. Now, so at omega equals omega p, that is at the passband edge frequency, what is the value of the gain? That is, what is 20 log of magnitude? If we call that in general as k. Okay, so what is this 20 log of magnitude? If I call this term as a k, which is the decibel scale, okay, the decibels value. So at the passband edge frequency, just look here at the specifications. At omega equals omega p, the gain is nothing but kp, right? So in this expression of k, let us substitute at omega p the value of k to be equal to kp. So the left hand side is kp, that is equal to minus 10 log of 1 plus omega is now what? Omega p divided by omega c whole to the power 2n. So let us simplify this further. I'll bring that minus 10 down this side. So kp by minus 10 equals log of 1 plus omega p by omega c to the power 2n. Now finally here I want to get the expression for this. Okay, that's my aim. Omega p by omega c to the power 2n. So we have a log on the right hand side, right? It's log to base 10. So this can be written as 10 raised to the power minus kp by 10 equals 1 plus omega p by omega c to the power 2n. Using your rules of logarithm, we can write it in this way. From this, I'll now write down what is omega p by omega c to the power 2n. So that will be 10 raised to the power minus kp by 10 minus 1. Okay, we can call this as equation 1. In the same fashion, now we will take the stop band edge. Frequency. So on the same lines, at omega equals omega s, what is the value of k? It will be ks. Stop band gain ks. Again, let's go back and substitute in this equation. Okay, let's call this as equation 2. Okay, we'll call this expression as equation 1. So in equation 1, now we'll have to substitute at omega equals omega s, k equals ks. So what will you get? Left hand side, ks equals minus 10 log of 1 plus omega s by omega c to the power 2n. Again, let's write down what is omega s by omega c whole to the power 2n. So minus 10 to the left hand side, minus ks by 10 equals log of 1 plus omega s by omega c to the power 2n. Similar to the step what we did previously, this can be written as 10 raised to the power minus ks by 10 equals 1 plus omega s by omega c to the power 2n. Simplifying that further, it is omega s by omega c to the power 2n equals 10 to the power minus ks by 10 minus 1. So this is equation 3. This is equation 3. Now, let us divide equation 2 by equation 3. Okay, let's divide equation 2 by equation 3. Okay, so left hand sides. Left hand sides, you have omega p by omega c whole raised to the power 2n. You divide that by this term, or that means you can multiply by omega c by omega s to the power 2n. Right, that's the same thing. I've taken the reciprocal. Then right hand side, 10 power minus kp by 10 minus 1 divided by 10 power minus ks by 10 minus 1. So omega c gets cancelled on the left hand side and you will be left with omega p by omega s whole raised to the power 2n. The power is common, right? So omega p by omega s to the power 2n. Omega p by omega s to the power 2n. With this, we'll have to get an expression for n. So the only possible way we can simplify this is by taking the log again. Okay, so let's take log to base 10 on both sides. Log to base 10 on both sides. So 2n, I can write it, I can bring it down. Log of omega p by omega s equals log of 10 to the power minus kp by 10 minus 1 divided by 10 to the power minus ks by 10 minus 1. So now it's easier to write down what is the value of capital N, isn't it? Just put 2 log to the other side. 2 log to the other side. Therefore, capital N is going to be log of 10 to the power minus kp by 10 minus 1 divided by 10 to the power minus ks by 10 minus 1 divided by 2 log omega p by omega s. That is the expression for the order of a Butterworth filter. So these parameters, that is kp, ks, omega p, omega s, will be given to you and you'll have to substitute in this equation to obtain the order first, capital N. Once you know what is the order of the filter, you can find the poles of the transfer function and write down the transfer function. But that transfer function will be for a normalized filter. That is omega c. The cutoff frequency is 1 radian per second. But then we need a cutoff frequency of omega c. Okay, omega c. And how do you find this omega c is what we have to see next. See, because the frequency response of a Butterworth filter depends on omega c. Actually, for Chebyshev filter, it depends on omega p. So in that case, this additional step of omega c is not there for a Chebyshev filter. But for Butterworth, since the expression for the frequency response has an omega c in it, we'll have to find the cutoff frequency. So we can say that the cutoff frequency lies somewhere between omega p and omega s. Okay, somewhere in between, in the transition band between the pass band and the stop band. That's where the cutoff frequency is. The minus 3 dB frequency, that is the cutoff frequency. So how do we find that omega c for a Butterworth filter will be the next step. Okay, and your Kp and Ks values will be negative actually because the magnitudes are less than 1, isn't it? So Kp and Ks values will be negative. So we'll see that when we solve a problem. So omega s, if you have to find out the cutoff frequency, sorry, omega c, the cutoff frequency, what is it that we have to do? Now take your equation 2. What is your equation 2? Omega p by omega c to the power 2n equals 10 raised to the power minus kp by 10 minus 1. This is in the power. Sorry, minus 1 is here. Okay. Now there are 3 possibilities for us to consider omega c. Okay, we have 3 possibilities. One is we'll consider omega c to satisfy the pass band requirements. See, I told you the cutoff frequency lies somewhere between the pass band and the stop band. Okay, it could be closer to the pass band or it could be closer to the stop band, or it could be in between also. So one option is to take that the cutoff frequency satisfies the pass band edge frequency and therefore calculate that depending on omega p. Otherwise, we'll assume that it satisfies the stop band requirements and calculate using omega s. Otherwise, you can take the average of the above two. Average of 1 and 2. Average of 1 and 2. Is that clear? So, if the cutoff frequency satisfies the passband edge requirements, then calculate omega c using omega p. Otherwise, using omega s. Otherwise, take the average of the two. Okay, so usually in the problem, they specify what you have to do, whether the cutoff frequency satisfies the passband edge or the stop band edge or both. Okay, so accordingly, you have to select omega c. Otherwise, we just prefer to take the first option. If at all it is not specified in the problem, we prefer to take the first option. That is, the cutoff frequency satisfies the passband requirements. So what do I mean by saying passband requirements is you calculate omega c using omega p. That's all. So this equation 2 that we have written, can we write down the expression for omega c here? Yes. So first write down what is omega p by omega c. What is that? 10 raised to the power minus kp by 10 minus 1 whole raised to the power 1 by 2. That power 2n, I bring it onto the other side. So from this, what is omega c? You take omega c onto the other side. So it's omega p divided by 10 raised to the power minus kp by 10 minus 1 whole raised to the power 1 by 12. So we have used only omega p here, if you can see. We have used only the passband requirements and then calculated omega c. So usually we do this if it is unless otherwise specified. So this is the first option. Similarly, the second option is to use the stop band requirements. In that we'll have to use equation 3 to calculate omega c. So what is equation 3? Omega s by omega c to the power 2n equals 10 to power minus ks by 10 minus 1. So we'll do the same thing here and write down the expression for omega c. Okay, So omega s by omega c is 10 to the power minus ks by 10 minus 1 whole raised to the power 1 by 2n. So what is omega c here? Omega c is nothing but omega s by 10 raised to the power minus ks by 10 minus 1 whole raised to the power 1 by 2n. Okay, so that is the second option. Call this is equation 4 and this is 5. The third option will be to take the average of 4 and 5. Average of equations 4 and 5. So you'll have to calculate omega c with equation 4, again omega c with equation 5, and take the average of the two. That is the third option. So usually we don't make it this much complex. We just use equation 4. If it is not specified in the problem, we just use equation 4 to calculate the cutoff frequency using the passband characteristics or the passband edge frequency. Okay, so these two equations that we have derived now for capital N and omega c is important, which is a part of the design procedure. So far you've just learned only the design of the analog low pass filter prototype, normalized filter. Okay, analog normalized low pass filter prototype. So if you have to convert this into the other filters, you should know the transformations. Okay, so I've told you this before, right? So we have just learned how to design the prototype. What is the prototype in this case? Normalized low pass filter and analog. Normalized analog low pass filter. So to convert this filter to digital, we use bilinear transformation. Okay, that we have to learn. Then to convert the low pass to, see, this is also normalized low pass. To convert it to the normal filter, that is the low pass with the desired cutoff frequency, in your Hn of s. What is Hn of s? The normalized low pass filter. In this you'll have to put s as s by omega c. Only then you're going to get your desired low pass filter. Okay. So if you just look back and see what we have derived, I'll just take you to the previous transfer function that we wrote. So here we have designed the normalized transfer function, isn't it? That you have to keep in mind. Never forget that. See here, Hn of s. We have designed the normalized transfer function. Okay, this is what we have designed. But the low pass filter that will be given to you will be having some cutoff frequency omega c. So what you have to do in this Hn of s, replace s by omega c. So this is a transformation to convert the normalized low pass to the desired low pass filter. Then only you will get your transfer function of the low pass filter. Okay. So what we'll do is we'll take up an analog design problem first. So with that, all these expressions and writing the Butterworth polynomial and writing the transfer function, the normalized transfer function, all those things will become clear. Okay, then we will see the bilinear transformation, that is the digital transformation techniques to design the digital filter. Both sorts of problems can be asked. Sometimes they even ask the analog design, sometimes they ask the digital design. So you should be able to do both. Okay, analog design also is asked. So shall we take up a design problem then? And these derivations are also important. The derivations of the order and cutoff frequency is important. Okay, and how do you derive the Butterworth polynomial? All the derivations are important. Design an analog low pass Butterworth filter for the following specifications. So magnitude of h of s is less than or equal to 0.8. So instead of giving h of j omega, they have given it as h of s. It doesn't matter. It's the frequency response that they are talking about. Actually, h of j omega had to be given in this place. So it's a question paper problem. So I didn't want to change anything there. So magnitude of h of s less than or equal to 0.2. So for 0.6 pi less than or equal to omega less than or equal to pi. Okay. So according to the problem that is given to you, first write down the filter specifications. Write down the filter specifications. See, again, he's given the frequency range in 0 to pi. So that happens to be the digital specifications actually. Sometimes they do such things, but since he has told it's an analog filter, don't worry too much about that. Just consider that it is analog filter specifications and design the problem. Okay. Sometimes such things will happen. So if you want, you can write down the frequency response characteristic curve, and that will be clear sometimes. So the picture will be better. So low pass, and yeah, he's given you the magnitudes, right? So you have to find the decibel, because for our design, that is all the equations that we have for Butterworth is in decibels. Okay, so it's better to convert that first. So what is Kp? 20 log of 1 minus delta p, right? That is 0.8 in this case. 0.8 in this case. So for an IIR filter, how the specifications are going to be for the magnitude as well as in the decibel scale, both I have given you. You will have to refer that for the general one and compare that and write down. Okay, so it's between 1 and this value, means this is the value of 1 minus delta p, that is here, somewhere here. Okay, so this is 1 and this is 0.8. So the gain, the passband gain Kp, we find out as 20 log of this value. Okay, so what is this? This is omega p. This is stop band, omega s. Okay, so 20 log of 0.8. You can find out actually it will be around minus 1.94 decibels. Minus 1.94 decibels. Okay, so that is in what range? 0 to 0.2 pi, he says, right? So only up till this range. So this is your passband edge frequency. That is omega p. Omega p is 0.2 pi. Okay, 0.2 pi. Similarly, this magnitude he says is 0.2. That means that is the stop band ripple. Find stop band gain from that. So 20 log of 0.2. 20 log of 0.2. Because they are decimal values, your logarithm will be negative. So for this you should get around minus 13.98 decibels. So since he has given you the magnitude here, you have to convert it to decibels. Sometimes the decibel values are given directly, in which case you can write down Kp and Ks directly. Then what is your stop band edge? So it's between 0.6 to pi, he says, right? So 0.6 pi to pi somewhere here. So pass band, something stop band edge is 0.6 pi. 0.6 pi. That is the stop band edge. So we have the 4 parameters with us now, the filter specifications. So your very first step will be to find the order of the filter. That is capital N. Capital N. Write down the expression for capital N. Write down the expression for N. What is that? Log of 10 raised to the power minus Kp by 10 minus 1 divided by 10 raised to the power minus Ks by 10 minus 1 divided by 2 log of omega p by omega s. Substitute the values of omega p, omega s. So log of 10 raised to the power minus Kp. Kp is minus 1.94. So to the power 1.94 divided by 10 minus 1 divided by 10 raised to the power. Ks is minus 13.98. So you already have a minus there. So it becomes plus 13.98 divided by 10 minus 1. Denominator 2 log of omega p is 0.2 pi. Pi gets cancelled in the numerator and denominator. So 0.2 by 0.6. Yes, calculate that. Calculate that value. It is log to base 10. So when you're using in the calculators, be a little careful with that. So you should be getting around 1.708. 1.708 for the order. So 1.7 we cannot use for the order, right? Because the order has to be an integer. So always round it off to the next highest integer. Okay. Always round it off to the next highest integer. So the order is 2. The order of this filter is 2. So after the first step, yes, once you find the order, now you can write down what is the transfer function or you can also calculate omega c first and then write the transfer function. Okay, so omega c. So it's not specified in the problem, right? What is that it has to satisfy? The cutoff frequency. So let's say we take that it satisfies the passband requirements. You can just write a statement that the cutoff frequency satisfies the passband requirements. Therefore, omega c is calculated as omega p by 10 raised to the power minus kp by 10 minus 1 to the power 1 by 2n. Lot of complexity is not required in the filter design problems. You can just simply state that it satisfies the passband requirement and consider omega c. That is, you don't have to find the mean and all those things. That's what I'm saying. You can just make the statement and calculate omega c. Yes, do that. So omega p 0.2 pi divided by 10 raised to the power 1.94 divided by 10 minus 1 to the power n is 2, therefore 1 by 4. Simplify that. So that's around 4.46 radians per second. 4.46 radians per second, you're going to get omega c. Okay, yeah. Next, we can write down the transfer function of the normalized filter. So it's a second order filter. Therefore, what is the Butterworth polynomial for second order? Here I'm writing it directly, but then in the exam you'll have to derive this Butterworth polynomial. Okay, at least write the expression for the poles of the transfer function, what is the angle, etc. What you're going to substitute. Consider the left half poles. Okay, whatever we discussed previously, you will have to do it according to that. Here I'm just writing it directly because we have already derived the second order Butterworth polynomial. B2 of s square plus 1.414s plus 1. So this was derived, right? So the Butterworth polynomial is that what is the transfer function? H2 of s I'll write because n is 2 here. So this is the normalized transfer function. Normalized transfer function. H2 of s is 1 by B2 of s. So 1 by s square plus 1.414s plus 1. That is the normalized transfer function H2 of s. So after we have written the normalized transfer function, you have to convert it to the low pass filter with the desired omega c, what we have calculated. So one more step we need to do after this. Okay, so here you will have to write the calculation for the poles. Okay, that should be written in the exam. Don't write the step directly. Yeah, so the desired low pass filter, if I call it as LP of s, will be what? In the normalized transfer function H2 of s, replace s by omega c. That will transform the filter into the desired low pass filter. S by omega C. What is omega C? 4.46. So 4.46. In this expression, you will have to replace. So that's 1 by S by 4.46 whole square plus 1.414 S by 4.46 plus 1 plus 1. So you can simplify that. Take LCM and write it in a simplified form. Okay, so if you take the LCM and simplify and write this, you get around 19.89 divided by S square plus 6.3S plus 19.89. Okay. So that is the transfer function of the Butterworth low pass filter, analog filter that is asked. So transfer function we are writing, correct? Not the filter coefficients like we did in the FIR filter. We are writing obtaining the transfer function here, and it's, you know that once you obtain the transfer function, you can also find the filter coefficients. It doesn't matter, either one of them is fine. Filter coefficients, that is h of n, or the transfer function, or the frequency response, any one if you find, we can convert that to the other.